The objectives in this topic are find the domains of rational functions, use arrow notation, identify vertical asymptotes, identify horizontal asymptotes, and use transformations to graph rational functions. So rational functions are quotients of polynomial functions, just like a rational number is an integer over an integer. A rational function is a function over a function. So it looks like a fraction. It works like a fraction. P and Q are polynomial functions, and polynomial Q can't be zero because we can't divide by zero. The domain of a rational function is the set of all real numbers except the x values that make the denominator zero. So as always, domain is thought of as what we can have, and to get to what we can have, we have to consider what we can't have. In this case, we can't have division by zero. So in this example, we're going to find the domain of the rational function f of x equals x squared minus 25 over x minus 5. So again, rational functions contain division. Division by zero is undefined. We have to exclude from the domain values of x that cause the function in the denominator to be zero. In this case, we can't let x minus 5 equal 0. What would cause that? Well, if x minus 5 equals 0, add 5 to both sides, x equals 5. The x value of 5 is what we cannot have. So the domain is everything except 5. So in set builder notation, we can say the set of all x such that x doesn't equal 5. But in interval notation, we would have negative infinity to infinity with the value 5 excluded, removed from the interval. How do we accomplish that? We would have negative infinity up to but not including 5. The parenthesis means not including. And we would join that with 5, not including the 5, through infinity. Let's find the domain of x over x squared minus 25 now. Again, rational functions contain division. We can't divide by 0. That means in this case, x squared minus 25 can't be 0. We can factor and solve. X squared minus 25 would be x plus 5 times x minus 5. That clearly gives us the values negative 5 and positive 5 that we can't have. Or we could use the square root property, add 25 to both sides, take the square root of both sides, being careful that we know that the square root of 25 is plus or minus 5. So the two values we can't have are positive and negative 5. The domain would be all real numbers except those values. So in set builder notation, we could say the set of all x such that x doesn't equal negative 5 and x doesn't equal positive 5. Or in interval notation, we can do negative infinity to infinity, but remove negative 5 and remove 5. So negative infinity up to but not including negative 5. Union with the interval negative 5 to 5, not including either value. Union 5 to infinity, not including 5. One more. This time we're going to look at function h, which is x plus 5 over x squared plus 25. If we go ahead and set the bottom equal to 0 as we've been doing and solve, we get x squared equals negative 25 when we subtract 25 from both sides. The square root of a negative number is imaginary. specifically here plus or minus 5i. But that means that no real numbers give us 0. And that makes sense. If we take something and square it, that's at least 0 or positive. It can't be negative. And if we take this non-negative thing and add 25 to it, there's no way to get 0 on the bottom, not with real numbers. Since we can't get 0 on the bottom, there are no restrictions. The domain is all real numbers, negative infinity to infinity. Let's talk a little bit about arrow notation. We use arrow notation to describe the behavior of some functions. If we have x and then this arrow and then some value with a superscript plus, we read the arrow as approaches. And the superscript plus means from the right, from the positive direction. So this means x approaches a from the right. X approaches a with the negative superscript would be approaching a from the left, from the negative direction. Be careful. It doesn't mean that we go positive or that we go negative. It means that we are approaching from the positive or approaching from the negative direction, approaching from the right, approaching from the left. X approaches infinity means that x gets bigger and bigger and bigger without bound. It increases forever. And x approaches negative infinity means that x decreases without bound. It gets smaller and smaller. It goes more and more to the left forever and ever. So x approaches infinity means that x is going all the way to the right. X approaches negative infinity means that x is going all the way to the left. Now we're going to use arrow notation to discuss the definition of an asymptote. So an asymptote is basically a dotted line that we put in a graph that the graph will approach but never touch. It'll get closer and closer and closer to it forever, but it will never actually touch it. So we would say the line x equals a, this dotted vertical line, is a vertical asymptote of the graph of a function f if f increases without bound as x approaches a. So notice, as we approach this value from the right, the function is going to go up and up and up and up forever. As we approach this from the left, the function is going to go up and up and up forever. So when we talked about arrow notation, we talked about x approaching infinity, x going to the right, x approaching negative infinity, x going to the left. Well, if our f of x, if our function approaches infinity, that's going to be up forever. If our function approaches negative infinity, that's going to be down forever. Here, this is two examples of the function going up forever. Once from the right, from the positive direction, as x approaches a from the right, f of x approaches infinity. There's our arrow notation. As x approaches a from the right, f of x approaches positive infinity. And here in this one, as x approaches a from the left, from the negative direction, f of x goes up forever. F of x approaches infinity. As x approaches a from the left, f of x approaches infinity. Now, that's not the only definition of a vertical asymptote. Not only can we bend it up forever, we could also bend it down forever. As x approaches a from the right, f of x approaches negative infinity. Or as x approaches a from the left, f of x approaches negative infinity. F of x approaching negative infinity just means goes down forever. This here is shown from the right and from the left. So if that ever happens, that means we have a vertical asymptote. How can we find vertical asymptotes? Well, if f of x equals p of x over q of x is a rational function in which p of x and q of x have no common factors, that's important, no common factors, and a is a 0 of q of x, the denominator, then x equals a is a vertical asymptote of the graph. So vertical asymptotes happen at the zeros of the denominators. That's what's happening here. So if we have f of x equals x over x squared minus 1, we need to find the zeros of the denominator to find the vertical asymptotes. So x squared minus 1 equals 0. The one time I don't explain factoring first and they show it by factoring. How about that? We can factor x squared minus 1. That's a difference of squares. That's x plus 1 times x minus 1. Again, if you need some review material on factoring that you're expected to know, please reach out. We can see here that the values that make the denominator 0 in this factored form are -1, or I should say +1 and -1. X minus 1 equals 0 gives us x equals +1. X plus 1 equals 0 gives us x equals -1. So -1 and +1 are the vertical asymptotes. We also could have done x squared minus 1 equals 0, which means x squared equals 1, which means the square root of both sides, x equals plus or minus 1. But for asymptotes, it really is better if you factor everything first. And that's because, as it says here, there are no common factors in the numerator and the denominator. We wouldn't know that unless we look at it in factored form. If something factors and cancels away, it still plays into the domain, but it does not play into an asymptote. So you might say, in this example, the domain and the asymptotes are the same, but that is not always the case. Trying to figure out what's different between these two slides. I needed to click one more further. The difference is now we're going to show the graph. And we can see at -1, as we approach from the left, the function goes down forever. It approaches negative infinity. As we approach -1 from the right, the function bends up forever. It approaches positive infinity. As we approach 1 from the left, the graph bends down forever. It approaches negative infinity. As we approach 1 from the right, the graph bends up forever. It approaches positive infinity. So that means that x equals -1 and x equals +1 are vertical asymptotes for this graph. Now, this one doesn't look too different. We want to find the vertical asymptotes if any of the graph of the rational function x minus 1 over x squared plus 1. But it is actually quite different because, as we've seen before, when we have the sum of squares on the bottom, x squared plus 1, there's no way with the real numbers to get x squared plus 1 equals 0. Because if we had x squared plus 1 equals 0, that would be x squared equals negative 1, which would be x equals plus or minus I. We'd get imaginary zeros. So looking at this graph, there are no vertical asymptotes. And that's again because the denominator will never equal 0. If this had been x minus 1 over x squared minus 1, x squared minus 1 would factor to x plus 1 times x minus 1, and the x minus 1s would cancel, leaving us with 1 over x plus 1. We would only have a vertical asymptote of x equals negative 1 in that case. The domain would be x can't be positive or negative 1. The domain happens before we cancel. Vertical asymptotes happen after we cancel. Let's switch things up from vertical to horizontal. For horizontal asymptotes, we want to look at what happens in the long run. We want to look at what happens when x approaches infinity or x approaches negative infinity. So horizontal asymptotes are a little bit different than vertical asymptotes. Vertical asymptotes, I said, we never ever cross. There is a situation where we can cross a horizontal asymptote, though, because again, horizontal asymptotes are about what happens in the long run. So looking at this first picture, if we jump on and let x approach infinity as we go to the right forever, we see that we're approaching this value b. F of x approaches b, but it never crosses it, but it gets closer and closer and closer to it the closer we get to infinity. Likewise, swooping down as we approach infinity, this second picture also approaches b. It approaches from the top, though. Here in this third picture is what I was talking about before. This graph actually does cross the horizontal asymptote, but as we approach infinity, as we get closer to infinity, we have that action of approaching this value of b without touching it. So that means that we do have a horizontal asymptote, even though it crosses at some point. So horizontal asymptotes, very similar to end behavior. Let f be the rational function given by this polynomial over polynomial. We have an a polynomial on top, a b polynomial on the bottom. They have different degrees. The degree on top, the highest power is n. The degree on bottom, the highest power is m. Now I'm going to do condition 2 first because I love condition 2. If n equals m, if they in fact have the same degree, then the line is the ratio of the leading coefficients, a sub n over b sub m. And when we get to the examples, you'll see how nice that is when we have the same degree on the top and on the bottom. If n is less than m, if the degree of the top is less than the degree of the bottom, then the horizontal asymptote is y equals 0, or the x-axis. And if the degree of the top is greater than the degree of the bottom, if n is greater than m, then there is no horizontal asymptote. So we have three conditions that we need to keep straight here for horizontal asymptote. And you might be thinking, oh no, three things to remember. It's not that bad. If the degrees are the same, we take the ratio of the leading coefficients. If the top is smaller, then we have y equals 0. If the bottom is smaller, then there is no horizontal asymptote. Instead, we'll get a slant asymptote. We may or may not look at slant asymptotes in just a little bit. So let's find the horizontal asymptote of 9x squared over 3x squared plus 1. The degree of the top is 2. The degree of the bottom is 2. The degrees are the same. So the horizontal asymptote is the ratio of the leading coefficients. 9 over 3 is 3. So y equals 3 is the equation of the horizontal asymptote. Be careful, that 3 doesn't come from the fact that there's a 3 on the bottom. It comes from the fact that 9 over 3 equals 3. So here's what the graph of that actually looks like. And we can see there is, in fact, a horizontal asymptote at 3. Because as we go left forever, we approach that value of 3 from the bottom. And as we go right forever, we approach that value of 3 from the bottom. Next up, we're going to look for the horizontal asymptote, if there is one, of the graph of the rational function, 9x over 3x squared plus 1. This time, the degree of the top is 1 and the degree of the bottom is 2. The bigger degree is on the bottom, so that's y equals 0. Why is it y equals 0? Because that's the rule when the degree of the bottom is greater. And sure enough, there's our graph. As we go far left and as we go far right, we're approaching the x-axis. We're approaching y equals 0. Finally, if we take a look at 9x cubed over 3x squared plus 1, the degree of the top is 3, the degree of the bottom is 2. The degree of the top is greater. And that's the situation where we have no horizontal asymptote. If we look at that graph, we can see there is no horizontal asymptote. We are instead approaching positive infinity and negative infinity, depending on if we're going right or if we're going left. Earlier, I mentioned that this is kind of like end behavior. If we imagine that we had x cubed over x squared, that would cancel away and just give us x to the first power. Specifically, this would be a positive 9x cubed over a positive 3x squared, so it would give us positive 3x. The coefficient is positive. The degree is odd, so just like x cubed, it rises to the right and it falls to the left, just like when we did end behavior of polynomials. So when we have no horizontal asymptote, we follow end behavior. We've talked about the parabola for quadratics, the cubic shape for cubics, the absolute value shape, the square root shape. Here are a couple more shapes. And once we know the shape, we can use our translations. We can move them up, down, left, right, just like any other shape that we know. So 1 over x squared has, 1 over x has these two legs, one in quadrant 1, another in quadrant 3. This curve is called a hyperbola. Not a parabola, but a hyperbola. It is an odd function. It has origin symmetry. 1 over x squared is a weird-looking hyperbola with its legs in the first and second quadrants. It's an even function. It has y-axis symmetry. And remember, to move left or right, we add or subtract from the x. To move up and down, we add or subtract from the entire function. So let's use the graph we know of 1 over x to graph 1 over x plus 2 minus 1. Well, the minus 1 on the outside of the function means we're going to move down 1. And the plus 2 on the inside with the x, remember that plus 2 doesn't mean we move to the right, it means we move to the left. So this is moved left 2, down 1. So begin with 1 over x. It has 2 points that we know, 1, 1, and -1, -1. We know the asymptote is y equals 0. We're going to move that asymptote and those 2 points each down 1. And then we're going to move those 2 points left 2. Don't forget about that vertical asymptote. It's going to go left 2 as well. So from the original black line graph, we have this new red line graph of moving left 2. Our 2 points are now at -1, 1 and -3, -1. The vertical asymptote is now x equals -2. Horizontal asymptote hasn't changed because we've just moved left. And now we're going to move down 1. The 2 points are now at -1, 0 and -3, -2. Down 1 is subtracting 1 from each y-coordinate. Horizontal asymptote moved down 1. Vertical asymptote stayed at -2. So we've taken our 1 over x and we've shifted it 2 to the left and 1 down to give us 1 over x plus 2 minus 1. I would like to talk about rational functions and their graphs. Rational functions look like fractions, except in the top and the bottom, we have expressions instead of numbers. So an example of the most basic rational function is going to be a new parent graph of f of x equals 1 over x. It's the reciprocal function. And if we have a coordinate plane, this graph has this dotted line thing where the 2 axes are. And the graph is in 2 sections, one up here and the other down here. Now,
This graph is called a hyperbola. It has two legs. And we can see as this graph moves out this way, it gets closer and closer and closer to the x-axis, but it's never going to touch it. In other words, as x approaches positive infinity, y, or f of x, approaches what? As x gets closer and closer and closer to infinity, we get closer and closer and closer to the x-axis. F of x would approach 0. Over here, as x approaches negative infinity, as we move farther and farther to the left, f of x also approaches 0. It gets closer and closer to 0 without touching it. That's an A on the end there, hyperbola. So this is different than the end behavior of a polynomial function. Polynomial function, it either approached infinity or it approached negative infinity. It either rose forever or fell forever. With these rational functions, with the graphs of the hyperbolas, we're approaching this dotted line. It's not always going to be the x-axis. For instance, if we moved this graph up, the dotted thing that we get closer and closer to would also move up. This notation, as x approaches negative infinity, as x approaches positive infinity, we've done that notation before. But I want to introduce another notation as x approaches 0 with this little minus sign up here. The minus sign indicates from the negative direction, from the negatives. So this actually means as x approaches 0 from the left. I could do better than that. Negative from the negative direction means from the left. There we go. So as x approaches 0 from the left, what happens? As x approaches 0 from the left, we're going to get closer and closer to this line, but we're never going to hit it. But where are we going? As x approaches 0 from the left, we're getting closer and closer to x equals 0. We're never hitting it, but our y value is getting closer and closer to negative infinity. As we approach 0 from the left, we fall. We approach negative infinity. What about as x approaches 0 from the right? What do you think that notation is going to be? From the left, from the negative side was a little minus as an exponent. As x approaches 0 with a plus there means as x approaches 0 from the right. So as x approaches 0 from the right, we're swinging up. So from the right, f of x would approach positive infinity. So we approach x equals 0, this dotted line from the right. What happens to the graph? It's swinging up. Closer and closer we get to 0, the closer the output is going to get to positive infinity. So that's what asymptotes do. We approach, and get closer and closer and closer, and we never hit it. In fact, it's going to bend us up towards positive infinity, down towards negative infinity. And then as we're going outwards, it's going to bend, and we're going to approach 0 or whatever the horizontal dotted line will be. Now, I've been calling it a horizontal dotted line because I didn't want to introduce the true name yet. These dotted lines are called asymptotes. And we have 3 different kinds of asymptotes. We have vertical asymptotes. That's the vertical dotted line. We have horizontal asymptotes. That's the horizontal dotted line. And we're also going to have a slant, also called an oblique asymptote. That's a diagonal. And we have those instead of horizontal sometime. So we'll have vertical asymptotes and we'll have horizontal or slant asymptotes. And today we're going to identify them from graphs. We're going to identify them from their equations, and we're going to learn how we can graph these things. Okay, sorry about that. So let's look at this graph. Let's say we have one, two, three, four, five, six. This will be a vertical asymptote. And what would the equation of this vertical asymptote be? Well, if this was just a line, which is really all it is, 1, 2, 3, 4, 5, 6, and it hits the x-axis, this is x equals 6. And we're going to have a horizontal asymptote. Here. And what's the equation of this horizontal asymptote? Well, if it were a line, and it is just a line, it would be a horizontal line that strikes the y-axis at 4. Horizontal asymptote is y equals 4. Or another way of saying that in function notation would be f of x equals 4. So vertical asymptote at x equals 6, a horizontal asymptote of y or f of x equals 4. Let me go ahead and put in the legs of this graph, actually draw the hyperbola itself. The asymptotes are not part of the graph. They're just telling us where the hyperbola bends. Okay, so there's our hyperbola. There's the legs. Let's fill in these questions. As x approaches negative infinity, f of x approaches what? And then we'll fill in as x approaches positive infinity, f of x approaches what? As x approaches negative infinity, that means as x gets farther and farther to the left. Well, f of x is getting closer and closer to this horizontal asymptote. F of x is approaching 4, but it'll never hit 4. Asymptotes tell us where the function does not exist. Whatever this function is, if we were to put a whole bunch of different x values in, it'd get closer and closer to an output of 4, 3.9, 3.99, 3.999, 3.9999999, 3.999999999999999, but we're never going to hit 4. Over here, as x approaches positive infinity, as x goes farther and farther to the right, f of x also approaches 4. So the horizontal asymptote tells us basically the end behavior of the rational function. Here's a graph, a new one, of the function 1 over x squared. This hyperbola is a little weird because instead of being in opposite corners, we still have our same horizontal and vertical asymptotes as 1 over x. But these are in side-by-side sections. So as x approaches infinity and as x approaches negative infinity, f of x approaches 0. But as x approaches 0 from either the left or the right, f of x approaches positive infinity. As x approaches 0 from the left, f of x approaches infinity. As x approaches 0 from the left, it curves up. As x approaches 0 from the right, from the positive side, f of x also approaches infinity. Okay, just wanted to mention that. We might come back to that later. We might not. It might be one of the graphs we move around. We'll see. I want to start focusing just on vertical asymptotes for now and how we can identify them from a given function. Now, just to draw something out here, vertical asymptotes tell us, well, they strike the x-axis, so they're x equals lines. They would tell us things that x cannot be. In other words, the vertical asymptotes tell us what we can't have in the domain. And remember, domain of something like f of x equals 2 over x minus 3. What can't we have? Well, we can't have 0 on the bottom. So we take the bottom, we say it can't equal 0. If we solve, that means here x can't be 3. And if x can't be 3, 1, 2, 3, that means we'll put a vertical asymptote at x equals 3. What if we had more than one thing? What if we were looking at a new function g of x, and this was x minus 4 over 3x squared plus 5x minus 2? Well, we can't tell what our restricted values are because it's not in factored form. So step 1 is always going to be factor top and bottom. Rather than clutter this, I'm going to move off to the side to do my factoring. This is a 3x squared, so the airplane method tells me put in a 3x and a 3x. Since that's actually 9x squared, we know we're going to need a corrective step at the end. Something's going to divide away. A times c, 3 times negative 2. We need numbers that multiply to negative 6, add to positive 5. These numbers would be positive 6 and negative 1. So I'm going to put in plus 6 minus 1. The corrective step would happen here, dividing both by 3. That gives us x plus 2 times 3x minus 1, or whatever your preferred way of factoring is, but you will need to be able to factor that. And now we can see that x plus 2 can't be 0, but also 3x minus 1 can't be 0. Those would cause us to get 0 in the denominator. They would cause us to be undefined overall. So x can't be negative 2. Add 1. 3x can't be 1, so x can't be positive 1/3. So here we would have 2 vertical asymptotes, positive 1/3 and negative 2. On the graph, at negative 2, there would be a dotted vertical line. On the graph, at positive 1/3, there would be a dotted vertical line. 2 vertical asymptotes, what? Now, I'm not going to draw this exact one, but yeah, we can have 2 vertical asymptotes. This graph might look like this. Something hyperbolic will happen on the outsides, and then something kind of parabolic will happen in the middle. Finding points and plugging them in is going to be what helps us find these actual graphs. You may or may not get that far today. I think we might. I think we might. Let's find the vertical asymptotes here of k of x equals 4x squared over x squared plus 4. Well, if we try to factor the bottom, we can't. X squared plus 4, sum of squares, we can't factor that. In fact, we see if we take the bottom and set it equal or not equal to 0, let's set it equal. It'll be easier to show you what's happening if I say equals. What are the values of x that make this true? Well, x squared equals -4. We can't take the square root of a negative number in the real numbers. And when we're graphing, asymptotes have to be real numbers for us to be able to find them and put them on the graph. So this has no solution, which means there are no values that cause the bottom to be 0, which means this one has no vertical asymptotes. None. Okay, let's do one more. We're going to find the vertical asymptotes of x plus 4. I guess we'll give this a function name too. Let's call it h of x. There we go. H of x equals x plus 4 over 2x squared plus 20x plus 42. So let's factor the bottom. We have to find the places where the bottom equals 0 to find the values we can't have for x. If we factor the bottom, and I'll do this over here, 2x squared plus 20x plus 42. We need to factor the 2 out first. We see we have a common factor, bringing us to x squared plus 10x plus 21. If you don't factor the 2 out first, you won't get the correct factorization. We need numbers that multiply to 21, positive 21. We need them to add to positive 10. This is plus 3 and plus 7. So rewriting this in factored form, we have x plus 4 over 2 times x plus 3 times x plus 7. Now, take the bottom, set it equal to 0. Find these restricted values. This means 2 can't be 0, x plus 3 can't be 0, and x plus 7 can't be 0. 2 can't be 0. No duh. 2 can't be 0. It's always true. We don't get any values from that. It's not like it says 2x equals 0 and we have to solve. Over here, x plus 3 can't be 0. So if we subtract 3 from both sides, x can't be -3. If we subtract 7 from both sides here, we see x can't be -7. So even after saying I would make it equals 0, I ended up making it not equals anyway. It really doesn't matter. What you need to do is understand why you're setting this equal to 0. So whether you say equals 0, whether you say not equals 0, just remember you're doing this to find out what you can't have for x. these values would become vertical asymptotes. There will be an exception to that, but happens very rarely, and we'll look at an example later. But as of right now, these vertical asymptotes are going to happen at x equals 3 and x equals -3 and x equals -7. Again, that's not a solution to this equation. These are vertical asymptotes, -3 and -7. Now, let's move on to horizontal asymptotes. We're actually going to have 3 cases. One of 3 things is going to happen. If we have a rational function, f of x, and it has some numerator on the top, some denominator on the bottom. On top, we want to find the degree of n. On the bottom, we want to find the degree of d. We want to find the degree of the numerator. We want to find the degree of the denominator. So if the highest power is a squared, then the degree is 2. If the highest power is a fifth, then the degree is 5. The 3 cases then would be that the degree of the numerator is less than the degree of the denominator, or the degree of the numerator is greater than the degree of the denominator. And guess what? Maybe they're both the same. The degree of the numerator equals the degree of the denominator. Degree of the numerator less than the degree of the denominator. An example would be, hey, 1 over x. The degree of the top is 0. The degree of the bottom is 1. Degree of the numerator is less than degree of the denominator. And remember, we started out by looking at the graph of this function. The graph of this function had a horizontal asymptote at 0. Horizontal asymptote is going to be y equals 0, just like 1 over x. That's it. There's no other work for that. If the degree of the top is less than the degree of the bottom, the horizontal asymptote is automatically y equals 0, like 1 over x. And the graph of 1 over x can help you remember that. If the degree of the numerator is greater than the degree of the denominator, then the horizontal asymptote is going to be none. There's going to be a slant instead. And we'll talk about how we're going to find that slant, that oblique asymptote, when we get to an example where this happens. at the very least, when we get to one that asks for the slant asymptote, as opposed to is there not a horizontal asymptote. If the degrees are the same, this one's my favorite. The horizontal asymptote is going to be y equals a ratio. And it's going to be the ratio of the leading coefficients. And again, when we get to an example of this, I'm going to show you what y equals ratio of the leading coefficients is. This one is the easiest if you don't consider that the easiest. This really isn't so bad. This looks complicated, but when we're working through the three cases, more and more examples, you're going to see, okay, it's not hard. I just have to remember the cases. So let's look at f of x equals 8x squared plus 1 over x to the 4th plus 1. The degree of the top is 2. Highest power we have is a squared, so the degree is 2. The degree of the bottom is 4. Highest power we have is a 4th, so the degree is 4. When the degree of the top is less, that's just like 1 over x. Just like 1 over x, the horizontal asymptote would be y equals 0. That's all the thought that has to go into that. The degree is smaller on top, just like 1 over x. So just like 1 over x, it has a horizontal asymptote of y equals 0. Now let's say we have g of x equals 2x cubed minus 6x all over x squared plus 4. The degree of the top is 3. The degree of the bottom is 2. The degree is bigger on the top than on the bottom. So the answer to what's the horizontal asymptotes would be none. We would instead have a slant asymptote. And we're not going to find that here. None is an acceptable answer. All because the degree of the top was bigger. That means no horizontal asymptote. Let's look at h of x. This is going to be 8x squared plus 9x minus 5 all over 2x squared plus 1. This one, like I said, is my favorite. The degree of the top is 2. The degree of the bottom is 2. Highest power of both is an x squared. So to find the horizontal asymptote, here's exactly what we're going to do. It's going to be y equals a ratio of the leading coefficients. Those x squareds, what are the coefficients? 8 over 2. Horizontal asymptote of y equals 4. When the degrees are the same, the ratio of the leading coefficients gives us our horizontal asymptote. 8 over 2 is 4. You say, what? I say, yep. Now I want to look at this further. And I'm going to use some magic to clean this up a little bit, but I want to look at h of x again. There we go, magic, see? All that circling, all that mess is gone. We found that the horizontal asymptote was y equals 4, or f of x equals 4. Two x squared plus 1 on the bottom. This is going to be one of those ones that doesn't have a vertical asymptote. Remember that the horizontal asymptote, that's telling us what we approach for a function value, for a y value. In this case, we're approaching 4 as x approaches positive or negative infinity. So as we get farther out, we're getting closer and closer and never crossing it. But that doesn't mean anything on the inside. So this particular one kind of looks like this. We have no idea how to do this yet. And being able to graph this isn't actually going to be important. But as you can see, as we approach as we approach negative infinity, as x goes farther and farther to the left, we're going to get closer and closer to 4, but we're never going to cross it. Here, as we approach positive infinity, we're going to get closer and closer to 4, but we're never going to cross it. But in the middle, we actually do cross it somewhere. So a follow-up question that you might be asked is, okay, you found the horizontal asymptote. Where, if anywhere, does it cross the horizontal asymptote? And what we're going to do is set the function equal to our horizontal asymptote and then solve for x. So where do we cross the horizontal asymptote of 4 here? We would set the whole thing equal to 4 and solve. So let me move this up so that I have more room to work. 8x squared plus 9x minus 5 over 2x squared plus 1. Again, it's set equal to 4 because that was our horizontal asymptote. We want to start by clearing the fractions. We want to make this a straight line equation. We would multiply both sides by the 2x squared plus 1. That'll cancel that out here, and we'll be left with 4 times 2x squared plus 1 on the left. On the right, we'll just have the 8x squared plus 9x minus 5. And here we go. Time to start solving. Clear parentheses by distribution. 8x squared plus 4 equals 8x squared plus 9x minus 5. If we subtract the 8x from both sides, we're just left with 4 equals 9x minus 5. Add 5 to both sides, 9x equals 9. Divide both sides by 9, we get x equals 1. So where are we going to cross the horizontal asymptote? It's going to happen when x equals 1. Specifically, the point 1 what? 1, 4. And again, if I drew what this graph kind of looks like, isn't it fun when I have to draw? Okay. See, it'll cross it at y equals 4, and we just solved to find that that x value would be 1. So the 0.14. Okay. Graphing right now, not important. Being able to find that point, though, that is important. Find the horizontal asymptote, and if it asks you, hey, what point does it cross that? Set it equal to the number, solve to get the x value.